The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, welcome everyone. This is 6046 recitation. Just make sure you're in the right place. My name is Ling Ren. I'm one of the 10 TAs for this class. And we do have a second TA for this section. I think he's not here right now, but basically Shanken and I will be switching every other week. I want to remind you, just a heads up, this section is recorded for OCW purpose, but I think he's only recording us, the TAs. He will, you're not in the camera, okay? All right, so the only purpose we are here is to help you learn this very interesting and also very useful class. So don't hesitate to ask any questions or give us any feedback, like whether I'm going too fast or too slow, whether you want us to cover something that's not in the posted schedule, right? Or just anything we can help. All right, so let's get started. The two lectures in this week, in the first week, focus on divide and conquer. It is a class of algorithm that usually involves recursion in the algorithm description. And Professor Devadas gone through several algorithms, including weighted interval scheduling and a bunch of others. And he left several open problems. So we will answer those open questions in this section, and we'll also show you a new algorithm and analyze a bunch of other algorithms. So just to remind everyone what weighted interval scheduling is, in this problem, we are given a bunch of requests. Each with a start time and a finish time. And our goal is to find a subset of them that are compatible, meaning they do not overlap, and that have a largest combined weight. Okay, everyone clear about that? So an easier case is when the problem is unweighted, meaning that, or you can think of every task has the same weight. In that case, we can just solve it using a greedy algorithm. But when the problem becomes weighted, we have to use dynamic programming or recursion. And Srini introduced a simple one, a basic version in a class. Can someone remind us how that algorithm works? Any volunteers? Mm-hmm.
For the next interval.
Can you speak louder?
We pick the earliest finish time for the next interval. So we find the next non-conflicting interval
Mm-hmm.
that has the earliest finish time, and then we pick that.
So what's your name?
Dr. Sai.
Uh-huh.
Then again, is that weighted? Am I correct?
I think the version you described is for the unweighted case. In the unweighted case, we just schedule the earliest, the one with the earliest finish time, and then we remove all the incompatible ones and we keep going, right? That solves the unweighted version. If it's the weighted version, we need to use recursion. And remember, we break the problem into many sub-problems, and each one can potentially be an optimal solution. Does anyone remember that? Can you give it a try?
Sure. So we break into subproblems, which is the best solution from a certain point.
Mm-hmm.
And then we calculate that subproblem starting at all the different finish times.
Mhm.
We find the maximum of that.
Great. What is your name?
I mean,
What is your Amy?
I
mean, okay. I mean that let's just try everyone as our potential first request. Okay. So if we choose request J as our first, we get its weight, right? And then we're going to solve a subproblem. So let me call the original problem weighted interval scheduling with all the incoming requests. Now we choose J request as our first. Now we are left with a subproblem that starts after request J finishes. So I'll write that as Rj, where I define Rj to be the set of requests where their start time is later than the finish time of the jth request. Okay, just to repeat, we choose a request as the potentially the first request, and then we look at all the requests that start after it and solve a subproblem of that case. Then we take a max of all the candidates we have, and that's going to give us the optimal solution. Any question about this algorithm? Okay, so this algorithm runs in n squared time. Now we are going to try to optimize that and come up with a better algorithm. So in order to improve anything, we first want to identify the inefficiency in this algorithm. Right? So which part in the algorithm do you think is inefficient or silly, unnecessary? Go ahead.
So it's inefficient to look through every previous subproblem when we're trying to find.
So you.
We're trying to find the maximum for any particular subproblem.
Are you saying that we don't need to go through every of this case?
Yeah, we should. Well, we should be able to efficiently query for the right one.
Okay. I think you are definitely correct. So let me just go through what this algorithm does, and it will be more clear. So what this means is I'll choose the first request, request 1 as my first request. Then I'm going to consider only the requests that start after 1 finishes, right? That only leaves request 5. Potentially some others I didn't draw there. Okay? That's my first candidate in that max. My second candidate is I choose request 2 as my first request. Then I have to remove request 1 because it starts too early. And then I'm left with all the remaining requests. I'll solve that subproblem. That's candidate 2. Candidate 3, I choose request 3 as my first request. And then I have to remove 1 and 2 because they start too early. Oh, 4 as well. It also starts too early, right? Before 3 finishes. Everyone following that? So we are left with the remaining request. Okay? Is it more clear now? Go ahead.
So, candidate, I mean, if you start with 3, that's actually a subproblem of 2. So, you see that like you're doing a lot of extra work with this current algorithm.
Great point. So what's your name?
Andrew?
Andrew said we can potentially be solving many repeated subproblems, right? Because, yeah, we definitely don't want to do that. And that's actually the core idea, the one crisp idea of dynamic programming. Andrew, can you tell me what's the definition of dynamic programming? You don't remember? Anyone remember that? Go ahead.
You can just memorize subproblems and then look them up.
Exactly. So dynamic programming says we will break a problem into subproblems and subproblem into even more subproblems. But whenever we solve one, we should memorize or just remember its result and store it somewhere. And if you need it again, we'll just retrieve it, right, without resolving the problem. That's definitely a great point. So we can analyze the complexity of this algorithm later, because I want to touch on this more efficient algorithm first. And we'll see that even after Andrew's optimization, its runtime is n squared. So without that observation, if we are solving repeated subproblems, it will be a lot worse than that. Anything to? Yeah, go ahead.
You can also trim ones that get to the same place, so you don't need to explore two paths.
Sorry, say that again.
You don't need to explore two paths that get to both explore and free. Once they're both looking at free, then you only need to do the one that's more efficient to that point.
Okay, cool. Go ahead. Oh, the same thing?
Well, I have another one also. I think to get better than n squared, I think we need to make the observation that it's always fine to start a subproblem later. So if you decided you're taking a certain sequence of intervals as your first interval, and then you want to see how to continue from there, it's always valid to start later. Then maybe you had to. So that means that if we can efficiently, starting at any particular point, query for the maximum of any of the subproblems starting after that point, then we can.
Okay, great. Yeah, I think we are on the same page. So when I describe the steps of this algorithm, remember the third candidate, I choose this as my first, right? It makes 0 sense, because if I do that, I might as well put in 2 as well. Doesn't hurt, right? Everyone get that? So yeah, the idea is that we shouldn't try every possible request as my first. Some requests are just better, more suited to be the first request. And how we are going to do that? So apparently 1 can potentially be the first request, 2 can also be, but it doesn't make any sense for any request to come after that, because there's an earlier request, right? So the efficient algorithm, let's first sort them by their start time. We are going to consider the request that comes early first. So I have my entire problem here. Now I'm going to ask a question. Should I include request 1 in my solution or not? That's only 2 cases. So if I do not select 1 in my solution, what subproblem am I left with? Any idea? If I decide I will not include 1 in my solution. Yeah, exactly. Because it does, there's no conflicts anywhere. I'll solve a subproblem from 2 to n. If I do decide to put my request 1 in the solution, I get its weight. So what's the subproblem I'm left with? Yeah, in this example, it's 5, correct? But more generally,
the way you define RJ, so every request that starts after 1 finishes.
exactly, every request that starts after 1 finishes. Okay. Now suddenly we are not breaking the original problem into n subproblems. We only have 2 subproblems. So let me draw a recursion tree, which is a powerful tool in analyzing this sort of things. So we start with our original problem from 1 to n. And we have two subproblems, 2 to n and R1 to n. This one, we'll also break them into subproblems. So what is this one? Okay, I have my subproblem 2 to n, and I need to further reply the same trick.
There's only one child.
Mm-hmm.
It would just be because for WIS, the max of WIS 3.
Oh, sorry. Sorry, these are the two cases, right? Either I schedule, either I do not schedule my first, or I schedule it, and it's my first request, right? Now here, I'm left with this problem. Either I do not schedule it, or I schedule it as my first request. So what is this one?
Oh, it'd be 3 to n.
3 to n, right? Because now I'm asking the same question for 2. And here, I'll have R2 to n, so on and so forth. Now, let me point out the big difference for this version and for the basic version. So I'm starting with the request that starts first. If I do not do that, say if here I'm asking the question for 5, do I schedule 5 as my first or not? Then what happens? Then these two branches do not cover all the cases, right? Because I can potentially schedule it, but not as my first in the optimal solution. If I'm asking a question for a random request. However, if I start with the first request, first meaning it starts earliest, it will either be not scheduled or it will be scheduled and as the first, because it cannot be the second request in my solution. Any questions about this algorithm? Okay. Now this is algorithm. Let's analyze its complexity. So what's the overall complexity when we go all the way down, solve the entire original problem? Any guesses? What do you think? What do you think? Go ahead.
It should be n log n, because we're going to need to sort the intervals.
Mm-hmm.
And we're going to need to, for every interval, find the next interval that starts after it finishes.
Okay.
And we can do that for everything in n log n.
Cool. So, because the first step is sorting, which is n log n. Now, after I sort everything, the question I need to answer is how many unique subproblems are there, right, in this entire recursion tree. So I'm not going to solve the same problem twice. How many unique problems exist here? N of them, right? Just this left branch, okay? All the others will be one of these, right? So I can start from bottom, the bottom of the tree, and work my way up. And when I want to go take this step, I'll look up the result of this in one of the subproblems I've already solved. Okay? So actually, the recursion itself is only O of n.
I missed what
Questions?
you said. What is the sorting referring to? What is it?
Okay, so we need to start with the request that starts first, right? We need to decide whether we schedule it or not. And then we need to do the same thing for this request 2. It's the start earliest request in this subset. We always need to do that for all the subproblems. So the overall complexity is n log n. But if we only focus on this recursion step, our improvement is actually larger than that, because it went from n squared to O of n. So why is the original algorithm n squared? I think it also has only n unique subproblems, right? So do you agree that the original algorithm is n squared? Or do you think it's also O of n? Just focus on the recursion step.
In the
Go ahead.
original algorithm, you solve some problems up to n times. So that's why it's still O of n squared, because you solve the same thing n times.
But assuming I do not do that, assuming whenever I solve it once, I store the result somewhere, and I directly get it. Okay? Assuming I do that, what's the complexity? Go ahead. Uh-huh. You think it's O of n? So anyone think it's n squared? Because I think Srini said it's n squared. Okay, go ahead.
So yeah, like I think the original algorithm isn't still n squared because we're still doing O of n work for every subproblem improvement.
Exactly right. Yeah. So here, whenever we go up one step, I'm doing constant number of work. Right? I'm just comparing two numbers and taking the max. However, in the original algorithm, which is here, whenever I want to go one step up, there are n branches of the tree. So my total amount of work is like 1 plus 2 plus 3 plus n, right? Every step becomes harder when I go up. And this is n squared. Any questions about that? Okay, this is so much for our weighted interval scheduling. Now I'm going to transition to the next topic. So any question on this side in general for the scheduling problem? Do you have a question? No? Okay. Yep. Now let's turn to a second topic of this section, which is Strassen algorithm. Strassen algorithm is an efficient algorithm for matrix multiplication. And matrix multiplication is a really useful primitive, or it has applications in almost every area. Like I can think of circuit simulation, climate simulation, and physics, basically everything. Now, I actually had some experience with matrix multiplication because my undergrad research was improving matrix algorithms. And actually many matrix algorithms, including like inversion, solving equations, they all use multiplication as a primitive. So it actually comes down to improving matrix multiplication. And I tried very hard to just optimize this basic matrix multiplication. You take a row, you take a column, and then you get your answer for this spot. And everyone's familiar with that, right? I tried very hard, but it's still 100x slower than the best algorithm out there. So I finally looked it up, and I was completely mind blown when I know that matrix algorithm complexity is not n cubic. It's actually smaller than that. Is this a surprise to you? Anyone expect that before? And the technique the more efficient algorithm uses is exactly Strassen algorithm. Now that we're talking about divide and conquer, you can guess it must be a divide and conquer algorithm. And so does anyone have an idea how to divide the original problem? You want to give it a try? So are you familiar with tiled matrix multiplication or blocked matrix multiplication? Okay, can you tell us what that is?
Yeah, you can break it into like quadrants essentially.
Mm-hmm.
their identity or have it.
Okay,
Can multiply.
cool. So say this is our A and B, and we want C. We can break each matrix into 4 parts. I'll call this A11, A12, A21, A22, B11, B12, B21, B22. Same thing for C. Now, I would like someone to tell me what is C11 in this case. Go ahead. A12, B21. Yeah. And C12 is, just speak up. Don't be shy. Okay, this is also my first section ever in my life, teaching a recitation. I'm more nervous than you guys. What is C12? A11, B12, A12, B22, right? So the rule is the same as before, matrix multiplication. Compute this, we take this row, this column, and it gives us this. So, right, thank you. A12, B21, right, A11. Okay, and same thing, C21, we're going to take this row and this column, A21, B11, plus A22, B21, C22 is A21, B12, plus A22, B22, okay? Everyone understands this? Okay, great. So now we've broken up the original problem into several subproblems. We only need to do matrix multiplication here 8 times. And each of this matrix is half in size. Right? If the original algorithm is in cubic, now each subproblem is half n cubic. Then we have 8 of them. So the complexity is still n cubic. No improvement at all. So actually, to be more precise, we should, because we can further break up these matrices into smaller blocks. So to be precise, its complexity should be given by a recursion, right? 8 subproblems, each one half the size, plus, can anyone tell me, what's the merging complexity once I get all this? All the go ahead.
Just constant because you're adding, or?
Yeah, because I'm adding, but is it constant? I'm adding these 2 matrices.
For the base case or for each level?
Pardon?
Or for each level or for base case?
Yeah, for base cases, of course, constant. Okay. So maybe I'm not clear about this. What's the subproblem in this case? It's this multiplication operation, okay? And so these are the 8 subproblems I will solve. After solving them, I need to add them together. And adding 2 matrices, and each is size half of n, the complexity is, yeah, it's n squared. Basically n squared. Right? So to get a precise complexity, we should solve this recursion, but it will end up being the same thing as this intuition n cubic. Okay, so now this is the magic. So Strassen in 1969 came up with this algorithm. And
Where the squared comes from
each of these is a half n by half n matrix.
Okay.
Okay.
Okay. I didn't realize you were about to mention it.
Okay. Cool. So Strawson came up with this algorithm. He somehow defined M1 through M7 7 matrices in this way. I can't provide any intuition because I didn't come up with this. And somehow, with those 7 matrices, he can compute all the 4 submatrices in C. And it's not very interesting to check it because the algorithm is definitely correct. But let's just do one of them. Okay, how about this one? So C21 is M2 plus M4. It's M2 plus M4. So M2 have A12, B11, A22, B11. So there's M4, there's A22 minus B11. So that cancels out. Right? So we are left with A21, B11 plus A22, B21. That's the correct answer. So this is I guess it's a very clever algorithm. You have to work in that area for 10 years to come up with this. So that's not our concern. Our goal is to analyze this algorithm. What's the complexity of it? So does anyone understand this recursion? Can someone tell me what's the recursion for this part, for this Strawson algorithm? We have the original problem. And we have some, go ahead.
So since each of the M1 through 7 only require one multiplication,
Mm-hmm.
you'll need to solve 7 subproblems. So 7t n over 2 plus O(n) squared n 4.
Yeah, that's absolutely correct. Everyone gets this? So what Strawson did is he came up with the 7 matrices. Each one requires only one multiplication. So we have 7 subproblems instead of 8. And that's going to give us a benefit, an improvement. Now, so the question now becomes, how do I solve this recursion? Right? Given this recursion, how do I know its complexity? And same question there. Anyone want to give it a try? So that's going to be covered in the third topic. What can I erase? Which is master theorem. So master theorem does exactly that. All it does is, given the recursion A and T of n over B plus some work for merging, where A and B are constants, it directly tells you what Tn is in some cases. So I'll first write the formula. Master theorem actually has 3 cases. The first case is Fn is order n raised to c, where c is less than log b of a. Then master theorem says its complexity is theta log b of a. Second case, Fn is theta nc log k, where c is log b equal to b of a. Then its complexity is n raised to c log k plus 1. And you don't necessarily have to copy them because you can just find it anywhere. And the third case, you can imagine, is the other the only remaining case, which is Fn is large, is omega n raised to c, where c is greater than log b of a. Then master theorem says its complexity of the complexity of Tn is theta Fn. So intuitively, if Fn is not too much work, then it's basically this recursion, what recursion gives you. If Fn dominates, Fn is the biggest component, then Tn is roughly on the order of Fn, and there's a case in the middle. Now let's see why that is the case. I'll only cover one case here. So again, we are going to draw a recursion tree, because that is very useful in all the recursion problems. So we start with the problem of size n, and we break them into problem size n over b. So on and so forth. What's the size of this subproblem? Okay, so that recursion represents a class of recursive algorithm. Every time it breaks the problem, it reduces the problem size by a factor of b. So what do I have here? Go ahead. N over b squared. So on and so forth. So what is A in this graph? Go ahead. 3? Think so? 3. Right. A is just a branching factor of this tree. Right. I keep going. Finally, I will reach my base case. So my next question is, after how many levels of recursion will I reach a base case of size 1? Go ahead. Log b of log b of. Okay, so because here is n over b squared, next one n over b cubic, so on and so forth. So for the, say this last level is tth level, then the problem size is n over b raised to t. And we want that to be a constant. So what is t? Log b of n. Now this is the recursion tree. And we have that Fn amount of merging work to do. So here we have to do Fn work, right, to merge these A results to the solution of our problem n. And we have F. What's the merging work for this level, for this part of the tree? This is my problem size. N over b. Right, and we have A of them. Okay? So on and so forth. So then we know what is Tn. Let's just enumerate all the work we have to do. So on the first level, we have to do Fn. Okay, on the second level, A, F, N of B, N over B. And what's the next level? We have how many subproblems? Speak louder. A square subproblems, and each of them is n over b squared. And finally, I reach my last level. They are all base cases. So I have A raised to t of them, right? Because I define t to be my depth of the tree. And each of them is t of 1. Okay, so that's Tn. I'm not entirely happy with this formula because I have this beautiful pattern here, right? Except for that last guy. It's A, add 1A and divide 1B, blah, blah, blah. So I'm going to change this T into F. Can I do that? Because asymptotically it's the same, right? T1 is a constant, F1 is also a constant. Then I get my beautiful form where it's a sum from I equals 0 to T. What's in the sum? Go ahead. A raised to I, F n over di. Everyone gets that? Now you can roughly see why we have three cases. So let me deal with the first case. The first case says Fn is order n raised to c. Right? What does that mean? It means this guy here is sigma a raised to n, then this is what's in my f raised to c. Okay, there should be an order here, but everything has an order before it, right? So I just omit that. So it actually should be this. Okay. So this, because n raised to c is actually independent of this sum, I can pull it out. And what am I left with? Is that correct? Now this is a sum of geometric sequence. Right? We know how to solve that, right? But we need to check whether this ratio is greater or larger than 1, or if it's equal to 1. And what is this ratio? The case tells us. Right? So C is less than log B of A. That means if I B raised to C is less than B raised to this guy, which is A, right? So we know our denominator is greater than our, is smaller than our numerator. So this is it's an increasing sequence, right? So what we have is n raised to c, then that thing raised to t minus 1 divided by this thing minus 1, but they are all constants, right? Are everyone familiar with this formula of geometric sequence? Okay, so that's what we have. Next, we have t equals log b of n. That means b raised to t is n, correct? So then b raised to t is n, then we have raised to c, cancel them, they cancel out. What do we have? I want to make sure everyone is following. A raised to t. No questions?
Can you do that step again?
Okay, let me do that again. Okay, it's actually a raised to t, and then n over bt raised to c, right?
I mean, how did you get from the line above that?
This one to here?
Yeah.
Oh, it's the sum of geometric sequence. So if I have 1 plus q square plus all the way to qt, it's qt plus 1, I guess, or t, I don't remember very well, minus 1, then q minus 1. Okay, I guess this should be t plus 1, right? Okay, so this is what we were doing. So this is our q minus 1, and divided by q minus 1, they are all constants, so I don't care about them. So a raised to t plus this thing raised to c, but we said that b raised to t is equal to n, so we're just left with a raised to t. And what is t? T is log b of n. I can write it as log a of n over log a of b. Everyone familiar with that? That means log a of n log b of a. Okay, this one I flip them, so it. So this, what is that? That is n. Okay, we're done. Are we? Not exactly, because I have an order here, right? So everything is order. If you only care about order, big O, then it's fine. But that theorem says theta. So you have to prove it the other way, that it's no less than that. Okay? But I'm not going to do that. It's not very hard. Next, I'm going to apply this theorem to the two problems we left here. So let's apply master theorem to this recurrence. I think you are still looking at that side. So what is the A, B, C for this? A is 8, B is 2, right? And C is 2. Log B of A is 3. So that's the which case of the master theorem? Okay, so the theorem says it should be n raised to log B of A, which is 3. Okay? Now, what we have here, can I invite someone to do that for me? Want to give it a try? Yeah, go ahead.
Okay, so we have A equals 7, B equals 2, and C equals 2, like before. And now we want to see whether C equals 2 is less than log B of A, which is log 2 of 7. And pretty sure that's still the case. So we should just get n to the log 2 of 7.
Yeah, exactly. So yeah, log 2. Yeah, thank you. Let's give him a round of applause. So log 2 of 7 is definitely greater than 2. Why? Because log 2 of 4 is 2, right? So this happens to be n raised to 2.80 and many other digits, but it's less than n cubic. And just for knowledge purpose, this is no longer the best. It was the best when it was proposed, and well, researchers in that area has get it down to n raised to 2.35. I think 2.37 first, then 2.35. I'm not following the literature very closely, so maybe it's 2.34 now. Okay, so I should have one more thing to cover, but I think we are running out of time. Sorry about that. I can post. So the last thing we should do is remember we have this median finding algorithm where we have a recurrence, which is I think n over 5 with some seeding, and then plus this, right, and plus some theta n, and we want to solve this recursion, but we cannot apply master theorem, right? Apparently, it's not the right form, so we have to, so when master theorem doesn't apply, we have to study it case by case. Now, let me see if I have time to do that. Okay, I think I probably do. So to solve that case, first, can someone tell me what's the definition of theta? We have to go back to the definition to solve that. What does theta even mean? So if I say Fn is theta n, what do I really mean? Go ahead.
It's tightly bounded, so both are moving to go either side.
Great. So it means I can find some k1 and k2 such that this holds when n gets sufficiently large. Okay. So now we're going to do an induction. Assuming for all the small n less than capital N, my Tn is bounded by this k2 and k1 thing. Okay, then my next step is T of this capital N would be bounded. I'll do the right side first. Will be bounded by k2 and 5 seeding plus k2, like things in that in the second term, and plus another theta n. So we know that means it's bounded by some other number. I'll say a2 n. Okay, that's the definition of theta n. Then can I find, I want this to be, sorry, all of them should be capital N, capital N, capital N. I want this to be smaller than k2, capital N, right? Because this, so let me redo this first step. This is roughly 5 of k2 plus 7 over 10 k2 and plus a2 of n plus a bunch of constants that I don't care. I want it to be smaller than k2 of n. Can I reach that? Of course I can, right? If I select k2 to be greater than all we have here, right? What is this? This is 9 over 10 n, 9 over 10 k2 plus a2, right? So if I select k2 to be greater than 10 times a2, is everyone following that? When n is sufficiently large, Tn should be bounded by k2n, right? That's my, that's the induction. I'm assuming when n is smaller than capital N, I have solved them, so I can use these two, and I show the next step. So there's the other side, which is very similar. I'm not going to go through that. All right, so that's all for today. And just to quickly recap, we went through the weighted interval scheduling, and the Strassen algorithm, master theorem, and applying master theorem, and that a case study of a new recursion. Okay, thanks everyone for coming.